Large vision language models are rapidly becoming the backbone of everything from automated coding assistants to multimodal search engines. But with that adoption comes a critical vulnerability: visual prompt injection. An adversary can take a seemingly benign image, add imperceptible pixel-level perturbations, and force the model to output harmful instructions, leak private context, or completely hijack its behavior. The scary part is that these attacks are highly flexible. They don't just target explicit jailbreaks, they can manipulate the model under completely benign-looking queries. And while the research community has rushed to build defenses, most of them are blunt instruments. They either require heavy auxiliary models that crush inference speed, or they sanitize the image so aggressively that the model loses its ability to read text or reason about spatial relationships. But what if we stopped treating the adversarial image as a monolithic block of noise? What if we looked inside the embedding space and found out that the attack doesn't actually need the whole image to work? That's exactly what this research does. The authors propose a method called gradient-guided token masking, or GTM. It's a lightweight, inference-time defense that localizes the exact visual tokens driving the attack and neutralizes them with a single forward-backward pass. No retraining. No extra models. Just pure mechanistic understanding applied to defense. Let's break down how it works, why standard gradient attribution fails, and how a subtle shift in perspective gives us a theoretically grounded way to shut these attacks down. To understand GTM, we first need to look at how LVLMs process images. An input image goes through a vision encoder, usually a vision transformer, and gets broken down into a sequence of embedding tokens. These tokens are then projected and fed alongside text embeddings into the language model. The model predicts the next token auto-regressively, conditioning on both the text history and the full visual embedding sequence. When an attacker creates a prompt injection image, they're essentially solving an optimization problem. They want to find a perturbed image that maximizes the probability of a target output sequence, all while staying within a tight perturbation budget, like an L-infinity norm constraint. The resulting image looks identical to a human, but the model's internal representation has been subtly warped to steer generation. Now here's the critical insight. The authors ran a sliding window masking experiment. They took adversarial images, systematically zeroed out contiguous blocks of embedding tokens at different positions, and measured how the attack success rate changed. The result was striking. For most masking positions, the attack succeeded just as well. The ASR barely budged. But when the masking window covered a few specific narrow intervals, the attack collapsed. The ASR dropped to near zero. This reveals a fundamental asymmetry in the embedding landscape. Adversarial capability isn't distributed uniformly across the image. It's highly sparse. The attack only needs a tiny subset of critical tokens to hijack the model. This means we don't need to sanitize the whole image. We just need to find those critical tokens and neutralize them. But how do we locate them efficiently? The intuitive answer is gradient-based attribution. If we compute the gradient of the adversarial loss with respect to each image embedding token, the tokens with the largest gradient norms should be the ones driving the attack. Here, where standard approaches hit a theoretical wall. A common shortcut is to only compute the gradient of the first generated token's log probability. It's fast, but it fails catastrophically under a condition called token alignment. Token alignment happens when the attacker's target sequence starts with the exact same token the clean model would naturally predict. For example, if the clean model would naturally start with I, and the attack also forces I as the first token, the gradient of the log probability becomes completely non-discriminative. Mathematically, under token alignment, the gradient of the first token log probability is dominated by the model's generic language modeling prior for that token. The actual adversarial signal that drives the subsequent harmful tokens gets buried in a negligible higher-order term. The attribution metric sees a high gradient, but it's just reflecting the model's normal text prior, not the injection trigger. You end up masking random semantic tokens instead of the adversarial ones, leaving the attack fully intact. So how do we recover the adversarial dynamics when output probabilities lie to us? The authors shift the attribution perspective from the final output space to the internal feature representation space. Instead of looking at the gradient of the log probability, they look at the gradient of the hidden state norm. Specifically, they take the hidden state at the last layer, right before the model predicts the first token. Let's call this vector H1. They then compute the gradient of the L2 norm of H1 with respect to each image embedding token. This becomes their saliency score. Why does this work? Because the hidden state H1 contains the compressed visual information that the language model actually uses to condition its next prediction. Even when the first token is aligned, the subsequent tokens in the target sequence still depend heavily on H1. By taking the chain rule, the gradient of the full sequence loss with respect to an image embedding can be approximated as a scaled version of the gradient of the hidden state norm, plus a small perturbation term. This isn't just heuristic. The paper proves a theoretical guarantee. Under standard assumptions about local linearity and bounded perturbations, the relative ranking of token importance derived from the hidden state gradient is asymptotically consistent with the ranking from the full adversarial loss gradient. In plain terms, if token O is more important than token B for the attack, the hidden state metric will correctly rank A above B, even when logic-based gradients fail. This gives us a mathematically sound way to identify the critical tokens without backpropagating through the entire target sequence. With that metric in place, the defense mechanism is straightforward. When an adversarial image comes in, the model runs a partial forward pass to get H1. Then, a single backward pass computes the hidden state gradient norm for every image embedding token. The top K tokens with the highest scores are identified as the adversarial drivers. These tokens are simply zeroed out or replaced with a mean embedding, and the sanitized sequence is fed back into the model for generation. The whole process requires exactly one forward-backward pass. No iterative purification. No diffusion models. No retraining. And empirically, masking just 5% of the top-scoring tokens is enough to collapse the attack. The results across multiple attack families and model architectures are striking. Against VMA attacks, which target manipulation, privacy breaches, watermarking, hijacking, and denial of service, GTM reduces the attack success rate to 0 across QN2VL, Phi3 Vision, and LLaVA v15. Against ImgHijack, which uses diverse perturbation constraints like stationary patches, moving patches, and unbounded L-infinity noise, GTM consistently drives ASR below 1%. And against advanced gradient-based optimizers like APGD and MIFGSM, it outperforms existing robust defenses like ASDRA and GUARD, especially under tighter perturbation budgets. But defense is only useful if it doesn't break the model. This is where GTM really shines compared to alternatives. Methods like diffpure, which try to purify the image through a diffusion process, achieve low ASR but severely degrade model utility. They destroy text and images, which tanks performance on OCR-heavy and spatial reasoning benchmarks like MMVet. GTM, by contrast, leaves benign visual information completely intact. The utility curves overlap almost perfectly with the undefended baseline, while still neutralizing the attack. Computationally, GTM is equally efficient. The undefended baseline runs in about 3.3 seconds, with 15.7 gigabytes of GPU memory. GTM adds a single backward pass and runs in 3.5 seconds at 17 gigabytes. Compare that to GUARD, which takes over 25 seconds, or diffpure, which pushes memory usage up and adds heavy latency. GTM is plug-and-play, target-agnostic, and requires zero training data. What makes this work particularly valuable for the broader AI safety community is how it reframes defense. Instead of treating adversarial examples as dense, global corruptions that require global purification, it recognizes that attacks are structurally sparse. By leveraging mechanistic interpretability to locate the exact embedding tokens that carry the adversarial signal, we can neutralize threats surgically rather than bluntly. This approach doesn't just protect against known attack vectors. Because it relies on gradient-based attribution of internal representations rather than attack-specific signatures, it generalizes to unseen prompt injection objectives and adaptive attackers. It also sets a precedent for how we should think about multimodal safety. Understand the internal dynamics, identify the minimal set of features driving the vulnerability, and intervene at the representation level. The code and experimental protocols are publicly available, which means the community can immediately benchmark new attacks against this defense and iterate. As multimodal models become more deeply integrated into critical workflows, lightweight, theoretically grounded defenses like GTM will move from academic exercises to infrastructure requirements. If you're working on multimodal safety, adversarial robustness, or mechanistic interpretability, this paper is a must-read. It shows that sometimes the most effective defense isn't about building bigger walls, but about understanding exactly where the crack is and plugging it with surgical precision. Thanks for watching. If you found this breakdown useful, check out the paper link in the description, and let me know in the comments what other multimodal defense mechanisms you'd like to see dissected next.